In a quiet laboratory, a scientist looks down at something that appears to have gone wrong. A culture plate has been contaminated. A photographic plate carries a mark it should not have carried. A receiver hums with a signal that refuses to disappear no matter how carefully the equipment is checked. At first, these moments do not look like history. They look like inconvenience. They look like failed technique, bad timing, dust noise, spoiled samples, mistaken assumptions, or results too strange to trust. In the clean legends we inherit, later discovery often arrives like a flash of brilliance. One person sees what no one else could see, names it, and the world changes. But inside the actual rooms where science happens, the beginning is often much less certain. A famous discovery rarely feels famous at the moment it first appears. Penicillin was not born as a finished medicine. X-rays did not arrive with a full explanation attached. Radioactivity was not waiting politely under its modern name. The echo of the early universe did not announce itself as cosmology. It sounded at first like a problem in an antenna. This is the hidden side of scientific discovery, the part before the textbook sentence, before the Nobel lecture, before the polished story, becomes easy to remember. It is the part filled with wrong guesses, stubborn instruments, confusing data, rejected ideas, missed meanings, and people who did not yet know whether they were looking at a breakthrough or merely at another thing that had gone wrong. And yet this messiness does not make science weaker. In a strange way, it is part of what makes science powerful. The great strength of science is not that it avoids failure. It is that it gives failure somewhere to go. A spoiled plate can be examined. A strange image can be tested. A failed prediction can become a clue. A result that makes no sense can remain on the table long enough for someone to ask a better question. So tonight we are going behind the clean legends of famous discoveries and into the slower, dimmer rooms where truth first appeared in disguise. How many breakthroughs began as mistakes? And if science is built through so much error, doubt, and correction, why has it become one of humanity's most reliable ways of approaching the truth? A famous scientific discovery is often remembered as if it happened in a single bright instant. A person looks down at an object, notices something no one else has noticed, and suddenly the world is different. The story becomes clean enough to fit into a paragraph, then a classroom, then a symbol. A moldy dish becomes penicillin. A glowing screen becomes X-rays. A strange photographic stain becomes radioactivity. A stubborn hiss inside an antenna becomes the echo of the early universe. From a distance, these stories seem almost effortless. They feel as if truth had been waiting just behind a curtain, needing only one gifted mind to pull it open. The scene is usually simple, the meaning clear, the discovery inevitable. The scientist appears calm, certain almost outside ordinary human confusion. But the real rooms were not so clean. The real rooms had cluttered benches, imperfect instruments, tired eyes, bad assumptions, and results that did not know how to explain themselves. They had samples that spoiled plates, that contaminated wires, that misbehaved photographic films that darkened for the wrong reason, and signals that looked like irritation before they looked like revelation. They had people who were not sure whether they were seeing a doorway or a defect. This is where many famous discoveries truly begin, not in triumph, but in uncertainty. Before a discovery becomes a legend, it is usually just a disturbance. Something does not fit. Something appears where it should not be. Something refuses to disappear after every ordinary explanation has been tried. At first, it may not look profound. It may look like a mistake in technique, a failure of cleanliness, a damaged plate, a badly shielded apparatus, or a question too small to matter. Think of a laboratory after a long day of work. The benches are not arranged for a museum photograph. There are labels written in haste glassware, waiting to be cleaned, notes that make sense only to the person who wrote them, and small practical frustrations that never appear in the final paper. Science from inside the room is not a procession of polished conclusions. It is a series of attempts to make nature answer, followed by the difficulty of understanding what answer was actually given. Sometimes the answer comes in the wrong language. A scientist asks one question, but the experiment quietly answers another. A researcher looks for a known effect and instead meets an unknown one. A tool designed for one purpose reveals a world it was not built to reveal. At such moments, the hardest task is not only to observe, but to notice that the observation deserves to survive. Many things in science are supposed to be discarded. Contamination is usually contamination. Noise is usually noise. A failed prediction is usually a sign that something must be checked again. Much of good scientific work depends on cleaning away error, controlling variables, repeating measurements, and refusing to be fooled by accidents. Without that discipline, every strange result could become a fantasy. But sometimes the thing being cleaned away is not the error. Sometimes it is the beginning. That is what makes the history behind famous discoveries more fragile than the legends suggest. Nothing about the first moment guarantees recognition. The scientist does not stand before a glowing sign that says, "Here is the future." Instead, there is only a result that sits awkwardly inside the expectations of the time. It may be too small, too strange, too inconvenient, or too difficult to explain. A mold on a bacterial culture plate can be thrown away. A darkened photographic plate can be blamed on poor storage. A glow in a dark room can be treated as leakage from some known source. A background hum in a receiver can be chased as an engineering problem. A measurement that finds nothing can be considered a disappointment. Only later does the story change shape. Later, after the testing, after the argument, after the repeated observations, after the hard work of other people, after a new language has formed around the event, the beginning is made to look clean. The uncertainty is compressed. The years of delay are shortened. The people around the edges fade. The failed interpretations vanish. What remains is a beautiful line from ignorance to knowledge. There is comfort in that kind of story. It gives discovery the shape of destiny. It lets us believe that truth once seen announces itself clearly. It makes science feel like a gallery of decisive moments, each one lit from above. But science is not built only from decisive moments. It is built from the long, unsettled period before decision is possible. In that period, the scientist is not simply a genius recognizing truth. The scientist is also a worker inside uncertainty, deciding what to keep, what to repeat, what to doubt, and what to ask next. A discovery may depend on intelligence, but it also depends on patience. It depends on not moving too quickly past the thing that does not fit. This does not mean that every mistake hides a miracle. Most errors remain errors. Most contaminated samples do not become medicines. Most strange readings do not become cosmic evidence. Most wrong ideas do not secretly contain a revolution. The danger of telling stories about famous accidents is that they can make science sound magical, as if carelessness itself were a path to greatness. The truth is quieter. Failure becomes useful only when it is brought back into a discipline of attention. The spoiled plate must be examined. The unexpected glow must be tested. The strange signal must be traced through every possible source of interference. The idea that fails must fail clearly enough to reveal what was wrong with the old expectation. Without that slow labor, accident remains accident. This is why the clean legend is not exactly false, but incomplete. Fleming did notice something unusual. Röntgen did follow an unexpected glow. Becquerel did see that a photographic plate had been marked in a way his first explanation could not handle. Penzias and Wilson did keep returning to a signal that would not go away, but none of those moments carried their full meaning at once. The famous scene is only the visible tip of a much longer process. Below it lies everything that makes the discovery real: repetition, doubt, interpretation, collaboration, correction, and the slow transformation of an odd result into knowledge others can test. A discovery is not complete when one person sees something. It becomes scientific when that something can survive being questioned. That survival is one of the deepest reasons science remains powerful despite all its failures. Science does not ask us to trust a result because it arrived dramatically. It asks whether the result can be examined, challenged, repeated, measured, and placed in relation to other things we know. In this sense, failure is not outside science. It is one of the tools by which science learns where its own ideas are weak. A failed experiment can close a false path. A failed prediction can expose a hidden assumption. A failed theory can leave behind methods, instruments, or questions that still matter. A failed attempt to remove noise can reveal that the noise was not noise at all. This makes scientific progress less like a straight road and more like a landscape gradually mapped by wrong turns. The wrong turns matter because they show where the ground is solid and where it gives way. They do not all lead directly to truth, but they change the shape of the search. The public version of discovery often removes this landscape. It gives us peaks without valleys, conclusions without hesitation, names without networks, success without the long apprenticeship of error. That is understandable. Human memory prefers stories it can hold. A single face, a single year, a single object. These are easier to remember than a web of partial contributions and unresolved doubts. But when the messy parts are removed, something important is lost. We lose the feeling of how difficult discovery really is. We lose the sense that knowledge had to struggle through confusion before it became obvious. We lose the many hands that steadied the process, the many failed attempts that sharpened the question, and the many earlier assumptions that had to weaken before a new idea could stand. We also lose a more honest kind of wonder. The polished legend makes discovery impressive because it seems sudden. The messy history makes it impressive because it shows how easily the moment could have vanished. A different habit, a different assumption, a faster cleanup, a less patient observer, and the clue might have disappeared back into ordinary failure. This fragility gives the stories their quiet tension. Imagine the contaminated plate before it becomes famous. It is not yet a symbol of modern medicine. It is just one object among many, something that appears to have been compromised. The ordinary response would be to clear it away and begin again. Good laboratory practice often demands exactly that. Now imagine the faint glow in a darkened room before anyone knows the name X-ray. It is not yet a revolution in medicine and physics. It is simply a screen behaving strangely near an apparatus whose effects are not fully understood. It could be leakage. It could be carelessness. It could be nothing. Imagine the photographic plate marked by uranium salts before radioactivity has a name. It is not yet part of a new understanding of matter and energy. It is a puzzling stain that does not sit comfortably inside the explanation that was expected. Imagine the persistent hum in the Bell Lab's antenna. It is not yet the cosmic microwave background. It is an annoyance, a stubborn signal in a machine built for precision. The first task is not to celebrate it, but to get rid of it. In each case, the beginning of discovery is almost indistinguishable from the beginning of cleanup. That is the doorway this documentary enters, not the public hall where discoveries are displayed after they have been named, awarded, and simplified, but the earlier room where the meaning is still uncertain. The room where a scientist may be tired, puzzled, skeptical, or simply trying to make an instrument behave. The room where truth has not yet become elegant. From there, the question changes. Instead of asking only who discovered what, we begin asking how a failed-looking thing survived long enough to become knowledge. What made someone pause? What made a result worth repeating? What kind of scientific culture allowed a mistake to be tested rather than merely erased? And what kinds of failure did science need in order to move beyond its own assumptions? The first answer is not dramatic. It is attention. Attention is slower than inspiration. It does not always feel heroic. It may look like checking a plate again, shielding an apparatus more carefully, repeating a measurement reading, an old paper, or refusing to force a strange result into a familiar explanation. It is the ability to remain with an inconvenience long enough for its shape to become clearer. But attention alone is not enough. A person can notice something strange and still misunderstand it. A result can be real and still remain unused. A discovery can appear and then wait years for the right method, the right community, or the right question. That is why the hidden failures behind scientific discoveries are not only personal failures, they are also failures of tools, language timing theory, and memory. Sometimes the room is messy because the bench is messy. Sometimes it is messy because the entire intellectual world is not yet arranged to understand what has appeared. This is where the clean legend becomes too small. It can tell us that a discovery happened. It cannot always show us what had to fail first: the original assumption, the experimental plan, the existing theory, the standard method, or the story later told about who mattered. To see that we have to move more slowly. We have to begin where discovery often begins, with something that looks as if it has gone wrong. In the next part of the journey, that something is a contaminated plate. It sits in the familiar story of penicillin as the almost magical object that changed medicine. But the plate itself was only the beginning. The hidden story is what happened afterward, the long, uncertain distance between noticing that bacteria had died and turning that observation into a medicine that could survive the body, the hospital, the factory, and the world. That distance is where the legend becomes human. The contaminated plate is one of the most familiar objects in the history of science. It has been told so often that it almost feels like a small myth. Alexander Fleming returns to his laboratory, notices mold growing on a dish of bacteria, sees that the bacteria around it have died, and from this accident, penicillin is born. It is a beautiful story because it is simple. A messy object appears on a bench, a careful eye sees meaning in it, and modern medicine begins to change. But the simplicity is deceptive. The plate did matter. Fleming's observation was real and important. Yet the story becomes much more revealing when we do not stop at the moment of noticing. Because the hidden failure behind penicillin is not that someone almost missed the mold. It is that even after the mold had been noticed, even after its antibacterial effect had been seen, the discovery still did not become a medicine for years. In the clean legend, the accident and the cure seem to stand almost side by side. In the real history, there was a long distance between them, and that distance is where the meaning of the story deepens. Penicillin did not move directly from a petri dish into hospitals. It had to pass through uncertainty, technical frustration, chemical difficulty, institutional delay, and the work of people whose names are less often attached to the miracle. The beginning was not dramatic in the way later memory makes it dramatic. Fleming was working with Staphylococcus bacteria that could cause infections. His laboratory at St. Mary's Hospital in London was part of a world still struggling against bacterial disease, with tools that often felt painfully limited. Surgery, childbirth wounds, pneumonia, blood poisoning, and small cuts that turned septic could all become dangerous in ways modern listeners may find hard to imagine. Before antibiotics, infection was not a minor complication. It was a shadow beside almost every hospital bed. Fleming already had a long interest in substances that might fight bacteria. He had discovered lysozyme earlier in the 1920s, an enzyme found in tears, saliva, and other body fluids that could dissolve certain bacteria. It was not the great therapeutic weapon medicine needed, but it showed his attention to the quiet chemical defenses of the body. He was not simply a man waiting for luck to fall onto his bench. He was already looking at the invisible conflict between microbes and the substances that might restrain them. Then came the plate. A culture dish had been contaminated by a mold. Around the mold, the colonies of bacteria seemed to have been dissolved or inhibited. Something in the mold was preventing the bacteria from growing. To many people, such a plate might have meant only that an experiment had been spoiled. In a laboratory, contamination is usually a nuisance. It interrupts order. It breaks the neat boundary between what was meant to be tested and what accidentally entered the test. Good science depends on controlling such intrusions. A contaminated sample is normally less useful, not more. It cannot be trusted in the same way as a clean experiment. It has been invaded by something unknown. But Fleming did not immediately discard it. That pause matters. It is not the whole story, but it is the first hinge in the story. He noticed that the contamination had created a pattern, and the pattern asked to be understood. The bacteria were not simply spoiled at random. They had been stopped in a zone around the mold. Nature had arranged by accident a little map of conflict on a glass dish. He identified the mold as belonging to the penicillium group, and he called the antibacterial substance penicillin. He tested it against different bacteria and saw that it was effective against some important types while not affecting others in the same way. He also recognized that it seemed relatively non-toxic to animal cells, which made it especially interesting. A substance that kills bacteria but spares the body is not just a chemical curiosity. It is the dream shape of a medicine. Yet dreams in science do not become real because they are promising. Penicillin was fragile. It was difficult to produce in useful quantities. It was difficult to purify. It seemed unstable, hard to concentrate, and hard to turn into something that could be reliably given to patients throughout the body. Fleming could see the biological effect, but the path from effect to treatment was not clear. The mold had opened a door, but behind the door was a corridor full of locked rooms. This is where the famous story often moves too quickly. To say that Fleming discovered penicillin is true, but it can make the discovery sound complete. It was not complete. What he had was an observation, a substance, a possibility. He published his findings in 1929, but the work did not immediately transform medicine. For much of the 1930s, penicillin remained known but underdeveloped, admired by a few, ignored by many, and technically frustrating to those who might have wanted to do more with it. It is easy from the future to judge this delay. We know what penicillin would become. We know that antibiotics would reshape surgery, wartime medicine, infectious disease treatment, and the expectations of ordinary life. We know that infections once feared as deadly would become treatable in ways earlier generations could scarcely imagine. Looking backward, the hesitation feels almost impossible. But at the time, penicillin was not yet the penicillin of history. It was one strange antibacterial substance among many scientific problems. It did not arrive with factory methods attached. It did not arrive with clinical protocols, stable preparations, large-scale fermentation, or a clear path through the bloodstream. It had to be made preserved, concentrated, tested, and trusted. A discovery that works beautifully on a dish can still fail when asked to enter the complexity of a living body. This is a crucial distinction. The Petri dish can show that something is possible. It cannot by itself build the bridge from possibility to medicine. For that bridge, the story moves to Oxford. In the late 1930s, Howard Florey, Ernst Chain, Norman Heatley, and their colleagues returned to penicillin with a different kind of urgency and a different set of skills. They were not merely repeating Fleming's moment. They were transforming a neglected possibility into a practical therapeutic agent. The work required biochemistry, pharmacology, animal testing, cultivation methods, purification techniques, and a willingness to wrestle with a substance that refused to behave conveniently. This part of the story is less suited to myth because it does not fit into one luminous scene. It is repetitive, technical, collaborative, and exhausting. It involves growing mold, extracting tiny amounts of active material, testing potency, improving methods, and trying again. It involves a kind of patient labor that history rarely turns into a symbol because there is no single object as memorable as the contaminated plate. But without that labor, the plate remains a fascinating accident. The Oxford group showed penicillin's power in animal experiments, including tests in which infected mice survived when treated with the substance, while untreated mice died. Even then, the problem of supply remained severe. Penicillin had to be recovered from culture fluid in painfully small amounts. Every drop mattered. Early human treatment revealed both the promise and the cruelty of scarcity. In one famous early case, a patient improved after receiving penicillin, but supplies ran out before the infection could be fully defeated. That moment exposes the hidden reality of discovery with unusual force. To have a medicine almost in hand, to see it work, and then to lose the patient because there is not enough of it, is not the kind of story that fits easily beside the neat legend of a moldy dish. Yet it belongs to the same history. It shows that science can discover a truth before society has built the means to use it. The failure is not in the observation. The failure is in the gap between knowledge and capacity. During the Second World War, that gap began to close. The need for better infection control gave penicillin new urgency. British and American researchers, universities, pharmaceutical companies, and government agencies worked to increase production. Better strains of mold were sought. Fermentation methods improved. Industrial scaling turned a difficult laboratory substance into a medicine that could be made in quantities large enough to matter. The transformation was not instant. It was not the work of one hand. It was a chain of attention, extending from Fleming's plate through Oxford's experiments and into industrial production. Each link required different kinds of intelligence. The microbiologist saw the effect. The biochemist tried to isolate and stabilize it. The experimentalists tested it. The engineers and manufacturers learned how to grow extract and distribute it. The miracle, if we want to use that word carefully, was not only the mold, it was the system that eventually learned what to do with the mold. This is why penicillin is such a powerful entrance into the hidden failures behind discovery. It begins with contamination, the very thing a laboratory usually tries to prevent. But its deeper meaning lies in the fact that noticing the contamination was not enough. The discovery had to survive years in which it was promising but impractical, known but not yet transformative, scientifically interesting but medically unfinished. A lesser version of the story says that Fleming found penicillin by accident. A fuller version says that accident provided a clue, and then science had to earn the discovery. That earning matters. It protects the story from becoming a lesson in luck. If penicillin were only a lucky accident, then science would seem almost passive, waiting for chance to drop gifts onto dirty plates. But the actual history shows something more demanding. Chance may open a door, but method must decide whether the door leads anywhere. Curiosity may pause over an anomaly, but technique must carry it forward. A strange result may begin the story, but community must make it durable. There is also a quieter lesson here about how discoveries are remembered. The human mind prefers a single discoverer and a single moment. It is easier to remember Fleming and the plate than to remember the long chain of people and processes that followed. It is easier to picture mold-killing bacteria than to picture years of purification work, animal experiments, wartime production problems, and chemical instability. The legend is not false, but it narrows the light. When the light narrows, some parts of the discovery fall into shadow. Florey and Chain are often remembered in more detailed histories, but even they do not complete the whole picture. Norman Heatley's practical ingenuity mattered deeply in the difficult work of extracting and producing penicillin. Other researchers, technicians, clinicians, patients, industrial workers, and institutions became part of the transformation. Medicine changed because a network eventually formed around an observation that had once sat almost alone on a laboratory bench. This does not take anything away from Fleming. It gives the discovery back its full human scale. Fleming's importance lies partly in his willingness to notice what others might have discarded. But the later importance of penicillin lies in the fact that the observation did not remain private, isolated, or merely interesting. It entered a wider process. It became something that could be tested by others, improved by others, manufactured by others, and finally trusted by doctors and patients far beyond the room where it first appeared. In that movement, we can see one of the central truths of science. A discovery is not only the first sighting of something new, it is the gradual conversion of that sighting into reliable knowledge. It must be separated from accident without losing what accident revealed. It must be purified from noise without erasing the signal. It must be made strong enough to travel. The contaminated plate was a beginning because Fleming did not treat it as meaningless. But the plate alone could not change medicine. It had to be followed by people willing to ask harder, less romantic questions. What exactly is this substance? How can it be extracted? How can it be kept active? How much is needed? How can it be delivered safely? Can it work inside a living organism? Can it be produced at scale? These are not the questions of legend. They are the questions of work. And in science, work is often where the miracle loses its shine, but gains its power. The plate becomes a process. The observation becomes a method. The method becomes a treatment. The treatment becomes part of ordinary medicine, so ordinary that later generations may forget how uncertain it once was. That forgetting is understandable. We live on the far side of the transformation. Antibiotics became so woven into modern expectations that it is difficult to feel the world that came before them. We have to slow down to remember a time when a wound could turn deadly, when pneumonia could carry a different terror, when surgery carried risks that no skill with a scalpel could fully control. Against that background, the contaminated plate becomes more than a lucky object. It becomes a reminder of how fragile the path from failure to discovery can be. A spoiled experiment could have been cleaned away. A promising substance could have remained too unstable. A published observation could have sat quietly in the literature and gone no further. A wartime urgency could have failed to gather the necessary resources. At many points, the path could have narrowed, stalled, or disappeared. Instead, the failure stayed alive long enough to be transformed. And that is the hidden shape behind the clean story. Penicillin did not succeed because failure was magical. It succeeded because failure was noticed, questioned, preserved, and eventually placed inside a disciplined system of experiment and production. The contaminated plate did not save lives by itself. It began a sequence of human attention that made saving lives possible. From this first object, the story of hidden failure now moves into stranger territory. A mold on a plate is visible. A zone of dead bacteria can be seen with the eye. But some discoveries begin with signs far less familiar. A glow that should not have been there. A photographic mark made in darkness. An invisible force passing through ordinary matter before anyone has a name for it. In those rooms, the problem is no longer contamination. It is light shadow and the unsettling possibility that the world is giving off signals human senses were never built to see. After the contaminated plate, the next doorway into hidden failure is darker. It is not a dish of bacteria, not a visible ring where life has been stopped by mold, not a biological clue sitting openly on glass. It is a room where light behaves wrongly. A screen glows when it should not glow. A photographic plate darkens when it should have remained untouched. Something unseen passes through barriers that were supposed to block it, leaving traces before anyone knows what those traces mean. The late 19th century was already filled with invisible things. Electricity had become more than a curiosity. Telegraph wires crossed continents. Lamps, motors, batteries, and laboratory instruments were changing the way people imagine nature. Scientists were learning that the world was not limited to what the eye could see. Forces could move through wires. Waves could travel through space. Matter itself could be probed with new devices that made the unseen leave marks. Still, there is a difference between believing the unseen exists and watching it appear where it has no right to be. In 1895, Wilhelm Conrad Röntgen was working with cathode ray tubes devices that had become common in physical laboratories. These tubes, partly evacuated of air and connected to high voltage, produced strange effects inside glass. They were part of a broader investigation into electricity matter and radiation, a world where experimenters often sat close to the edge of what their instruments could explain. Röntgen's discovery began not as a clean answer, but as an inconvenience in the room. He had covered the tube to block visible light. Yet nearby, a fluorescent screen began to glow. The glow should not have been there, at least not according to the ordinary explanation available in the moment. Something from the covered apparatus was traveling across the room and making the screen shine. At that instant, the finding could still have been reduced to a fault. Perhaps the covering was poor. Perhaps some ordinary light had leaked out. Perhaps the screen had been affected by something already known. A cautious scientist does not turn every odd effect into a revolution. The first duty is often to doubt the oddness. Röntgen did exactly that, but he did not dismiss it. For weeks he investigated the strange rays in private. He tested what they could pass through and what could stop them. Paper did not block them. Wood did not block them easily. Flesh was partly transparent to them. Dense materials, especially metal and bone, stopped them more strongly. Bit by bit, the phenomenon became harder to explain as a mere leak of ordinary light. The invisible had begun to draw pictures. One of the most famous early images was the hand of Röntgen's wife, Anna Bertha, in which the bones appeared as pale structures and her ring stood out sharply. The image was startling not only because it showed the inside of the body, but because it changed the emotional relationship between vision and matter. A living hand, familiar and ordinary, suddenly became a ghostly arrangement of bone shadow and metal. It is easy now to forget how unsettling this must have been. Today, X-ray images belong to hospitals, dental offices, airport scanners, and routine medical care. They are part of the background of modern life. But in the beginning, they belonged to a stranger world, a world in which a sealed tube in a dark room could send out something unknown, something that crossed through surfaces and returned with hidden structures. Röntgen called them X-rays because their nature was unknown. The X did not mean drama. It meant uncertainty. It marked a blank in understanding. That blank is important. The discovery was not born complete. It did not arrive with a full theory of electromagnetic radiation in medical practice, with safety standards, with clinical protocols, or with knowledge of long-term harm from exposure. It arrived first as, in effect, a new capacity of nature to make the invisible visible. The hidden failure here was not a failure of carelessness. It was a failure of expectation. The room behaved in a way the existing explanation could not contain. Röntgen had asked one kind of question about cathode rays and apparatus. Nature answered with something that expanded the question itself. The scientific power of the moment lay in the decision not to force the glow back into the old category too quickly. If the contaminated plate showed that life could leave a pattern of death around mold, the X-ray screen showed that matter could reveal its interior through an unknown form of radiation. Both began with a deviation. Both required someone to stay near the deviation long enough for it to become structured. But X-rays had a special swiftness once they were announced. The images were too vivid to ignore. Physicians, physicists, and the public quickly understood that something extraordinary had appeared. Within a short time, X-ray demonstrations spread widely, and medical uses began developing with astonishing speed. That speed brought promise, but also danger. In the early excitement, the risks of radiation were not fully understood. People exposed themselves too freely. Demonstrations could feel almost magical. The power to see beneath skin seemed so valuable, so modern, so astonishing, that the slower work of caution lagged behind the new ability. Here again, discovery did not arrive as pure triumph. It arrived with ignorance attached. The same invisible force that could help locate a fracture could also injure living tissue. The new sight carried a hidden cost. That does not diminish the discovery. It makes the discovery more real. A breakthrough does not simply give humanity a tool. It gives humanity a tool before humanity fully knows how to use it. The work of science continues after the first image through refinement, measurement, safety, and restraint. A year after Röntgen's discovery, another strange effect appeared in the history of invisible radiation. This time, the scene was not a glowing screen beside a covered tube, but photographic plates, uranium salts, and a question shaped by the excitement over X-rays. Henri Becquerel was studying substances that glowed after exposure to light, a property known as phosphorescence. Since X-rays had just stunned the scientific world, it was natural to ask whether some glowing materials might emit similar rays after being exposed to sunlight. The question was reasonable. It followed the logic of the moment. Becquerel placed uranium salts near photographic plates wrapped to keep ordinary light out. The expectation was that sunlight would excite the salts, and then the salts might emit something capable of affecting the plate. In this framework, the sun mattered. Light was supposed to awaken the effect. Then the weather interrupted. Cloudy conditions meant the planned sunlight exposure could not proceed as expected. Becquerel stored the materials away with the uranium salts and photographic plates still together. Later, when he developed the plates, he found that they had darkened strongly anyway. The expected chain of explanation had broken. The plate had been marked without the sunlight that was supposed to make the effect possible. At first glance, this could have been a failed experiment. The conditions were wrong. The planned exposure had not happened. The plates could have been treated as spoiled by circumstance, not as carriers of new information. But as with Röntgen's glow, the important thing was not merely that something strange occurred. It was that the strangeness was followed. Becquerel realized that the uranium itself was emitting something capable of penetrating the wrapping and affecting the photographic plate. The effect did not depend on sunlight in the way he had expected. It did not seem to depend on phosphorescence, as originally imagined. The material was giving off radiation on its own. This was a profound shift. With X-rays, the unknown radiation had been produced by an electrical apparatus. With Becquerel's uranium, the source seemed to be within the substance itself. Matter was not as quiet as it had appeared. Some materials seemed to carry an internal restlessness, sending out energy from within without being visibly changed by ordinary light. Again, the first explanation failed, and again the failure mattered. Becquerel had not set out to discover radioactivity as later generations would understand it. He was following a reasonable hypothesis inspired by a recent discovery. The experiment did not confirm that hypothesis. Instead, it opened a deeper one. The wrong expectation became the scaffold around an unexpected truth. This is one of the recurring patterns in science. A theory or assumption can be wrong in the precise way that makes a new observation possible. If Becquerel had not been thinking about X-rays and phosphorescence, he might not have arranged the materials in that form. If the weather had been clear, the story might have unfolded differently. If the darkened plate had been dismissed as a spoiled result, the clue might have waited longer. The discovery depended on a chain of imperfect circumstances. Soon Marie Curie entered this world of mysterious emissions and gave it a new depth. She studied uranium rays with remarkable discipline, measuring the strength of the emissions and asking whether the effect belonged to chemical compounds or to the atoms themselves. Her work suggested that the radiation was tied to the nature of the element, not merely to its chemical arrangement. She also investigated thorium, and with Pierre Curie pursued the substances that led to the identification of polonium and radium. The word radioactivity would become attached to this field, but the name came after the disturbance. The early evidence was not elegant in the modern sense. It was laborious, measured through instruments, residues, minerals, and the faint electrical effects produced by invisible emissions. It required patience with materials that seemed to be saying more than chemistry was prepared to hear. Pitchblende, the uranium-rich ore that became important in the Curie's work, appeared more active than uranium alone could explain. Something else was hidden within it. To find that something was not a single flash of insight. It was grinding labor, Tons of material, repeated separations, heavy vessels, chemical processes, measurements, and physical strain entered the story. If X-rays gave the world an image, almost instantly understandable radioactivity demanded a slower surrender to evidence. It asked scientists to accept that matter contained energies and transformations far stranger than classical intuition allowed. The hidden failure was expanding. It was no longer only a failed expectation about a glowing screen or a photographic plate. It was a failure of the older picture of matter as stable solid and essentially quiet. Radioactivity suggested that atoms, once imagined as the firm building blocks of the material world, held processes within themselves that could alter, emit, and decay. This had consequences no one at the beginning could fully imagine. The path from Becquerel's plate to nuclear physics, medical radiotherapy, atomic structure, and the later terrors and powers of nuclear energy was long, uneven, and morally complicated. It would pass through brilliant insights, dangerous exposures, incomplete safety, understanding, and discoveries whose applications would eventually become both healing and destructive. That complexity belongs to the story because it reminds us that scientific discovery does not control all the futures it opens. At the beginning, there is only a mark on a plate. There is something almost haunting about that. A photographic plate is supposed to receive an image from light. In Becquerel's case, it received the presence of something unseen. It became a witness before there was a language adequate to the testimony. The same can be said of Röntgen's fluorescent screen. It glowed before anyone could comfortably explain why. The hand image appeared before medicine had fully absorbed what such seeing would mean. The instruments did not wait for theory to become ready. They gave their evidence first. This is one reason that the hidden history of discovery feels so different from the clean legend. In the legend, discovery follows understanding. Someone knows what to look for, finds it, and names it. In the real room, evidence often arrives before understanding. It does not explain itself. It has to be held tested, doubted, and slowly interpreted. That can be unsettling. A strange glow can be beautiful, but it can also be a warning that the old boundaries are no longer reliable. A darkened plate can be exciting, but it also means that invisible forces are passing through coverings thought to be protective. A new power to see inside the body can heal, but it also teaches that seeing has risks. Every discovery widens the world, and a wider world is not always more comfortable. For the people living through these moments, uncertainty was not a decorative detail. It was the atmosphere. They did not yet know which phenomena would become medical tools, which would become new branches of physics, which would demand new safety standards, or which would change the conception of matter itself. They had clues, not conclusions, and still those clues had to be followed. The lesson from this part of the journey is not simply that X-rays and radioactivity were accidental. That is too thin. The deeper lesson is that science often progresses when an experiment fails to stay inside the question it was built to answer. The apparatus gives more than it was asked for. The plate records more than the theory predicted. The material behaves as if it belongs to a larger world than the one the scientist had imagined. At such moments, failure becomes a kind of opening, but only if someone resists the urge to close it too quickly. Röntgen did not dismiss the glow as a nuisance. Becquerel did not reduce the darkened plate to inconvenience. Marie Curie did not treat the strange activity of minerals as a minor chemical oddity. Each in a different way allowed the evidence to remain difficult. That willingness is rare and disciplined. It is not the same as believing every anomaly. It is the harder practice of testing an anomaly until either it dissolves into error or becomes too solid to ignore. The history of X-rays and radioactivity shows both outcomes living close together. There were wrong explanations. There was overexcitement. There was incomplete safety knowledge. There were instruments being asked to reveal things no one yet understood. But through that imperfect process, a new invisible architecture of the world began to emerge. The human body became seeable in a new way. Matter became active in a new way. The boundary between surface and interior, between stillness and energy, between darkness and evidence, began to shift. And all of it began with signs that could have been mistaken for something going wrong. From the contaminated plate to the glowing screen to the darkened photographic film, the pattern is becoming clearer. Discovery often begins when the world refuses to obey the small story prepared for it. A mold does more than spoil a culture. A covered tube sends out unseen rays. A uranium salt marks a plate without the expected light. The next strange signal will be even quieter. It will not appear as a glow on a screen or an image of bone inside flesh. It will not sit as a stain on a plate. It will come as a persistent noise inside a machine built to listen to the sky, a faint microwave hiss that two radio astronomers try again and again to remove. And the more they try to silence it, the more important it becomes. The next hidden failure did not appear as a stain, a glow, or a shadow on film. It came as a soundless irritation inside an instrument, a signal that should have been removable, but was not. It did not look like the beginning of cosmology. It looked like a technical problem, the kind of thing careful engineers are trained to identify, isolate, and eliminate. In the early 1960s, at Bell Labs in New Jersey, Arno Penzias and Robert Wilson were working with a large horn-shaped radio antenna. The instrument had been built for satellite communication research, a precise structure designed to receive faint microwave signals from the sky. It looked less like a telescope from an older age and more like a great metal ear lifted towards space. Radio astronomy had already taught scientists that the universe was not silent. Stars, galaxies, gas clouds, and other cosmic sources could speak in wavelengths no human eye could see. The sky was no longer only a field of visible points. It was a layered presence filled with signals that had to be translated by instruments before they could enter human understanding. But the signal Penzias and Wilson found was not what they were seeking. Their receiver registered a persistent background noise, an excess hiss that seemed to come from everywhere at once. It did not rise clearly from one star, one galaxy, one direction, or one obvious source on Earth. It was not dramatic. It was not shaped like a message. It was simply there, steady, unwanted, and difficult to explain. At first, it belonged to the category of things that must be fixed. This is important because good measurement begins with suspicion. A faint signal can come from the atmosphere, from the ground, from the instrument, from human activity, from heat in the receiver, from loose connections, from contamination, from ordinary imperfections hiding inside a system too sensitive to forgive them. Before a scientist can say the sky is telling us something, they must ask whether the instrument is only telling them about itself. So Penzias and Wilson tried to remove the noise. They checked the equipment, they examined the receiver, they considered possible sources of interference. They looked at the antenna, the surrounding environment, and the technical behavior of the system. They wanted a clean instrument, and the noise was preventing that cleanliness. It was an annoyance standing between them and the measurements they expected to make. Even the antenna itself became suspect. Birds had entered the horn antenna, and with them came nesting material and droppings. the kind of ordinary mess that belongs to the physical world, but not to the ideal version of scientific measurement. Penzias and Wilson cleaned the antenna. They removed the birds. They dealt with what they politely called the white dielectric material left behind. The noise remained. There is something quietly beautiful about that detail, not because it is funny, though history has often remembered it that way, but because it makes the scale of the story almost impossible to hold. On one level, two scientists are cleaning bird droppings from a radio antenna. On another, they are unknowingly trying to scrub away the afterglow of the early universe. The gap between those two realities is where the tension lives. If the noise had disappeared after cleaning it, would have joined the countless small corrections that keep laboratories functioning. It would have been forgotten, as most technical problems are forgotten once solved. But it did not disappear. Each ordinary explanation weakened. Each attempted correction failed. The unwanted signal began to change its nature, not because it grew louder, but because it survived. That survival is often where a discovery begins. At first, persistence is frustrating. Then it becomes interesting. Eventually, if the evidence continues to hold, it becomes dangerous to the old explanation. A signal that refuses to vanish begins to ask a different question. Not what is wrong with the machine, but what if the machine is working? This reversal is one of the deepest movements in science. The same caution that tries to remove error can, if carried far enough, reveal that the suspected error is not error at all. The discipline of doubt does not only destroy false clues, sometimes it protects true ones. By testing every ordinary cause, Penzias and Wilson gave the strange noise a chance to prove that it did not belong to the ordinary category. At about the same time, not far away in Princeton, another group of scientists was thinking about the early universe in theoretical terms. Robert Dicke, Jim Peebles, David Wilkinson, and their collaborators were considering the possibility that if the universe had once been much hotter and denser, then some remnant of that early fire might still be present. It would not appear as visible flame. It would be stretched by the expansion of the universe into a faint microwave background, cold, but not absent everywhere in the sky. The idea did not come from nowhere. Earlier physicists, including George Gamow, Ralph Alpher, and Robert Herman, had explored related predictions in the context of an expanding hot universe. But by the 1960s, the observational situation remained unsettled. Cosmology was still a field where large questions could remain open for a long time. Was the universe evolving from a hot, dense beginning? Or could it exist in a more steady state, continuously renewing itself over cosmic time? The noise in the Bell Labs antenna entered this debate without announcing that it was entering a debate. Penzias and Wilson were not setting out to settle the origin of the universe. They were radio astronomers dealing with a stubborn background signal. The Princeton group, meanwhile, was preparing to search for the very kind of cosmic remnant that Penzias and Wilson had stumbled upon. When the two lines of work connected, the unwanted hiss began to acquire a cosmic meaning. This is one of the most delicate aspects of the story. The discovery was not simply a matter of hearing the universe and knowing immediately what it meant. The signal and the interpretation had to find each other. Measurement alone was not enough. Theory alone was not enough. The noise needed a framework, and the framework needed evidence. When they met, the history of the universe changed shape. The signal became known as the cosmic microwave background, a faint radiation filling the sky, understood as a relic from an early stage of the cosmos. It did not show the first instant of creation in a simple visual sense. It was not a photograph of the Big Bang. It was more like an ancient afterglow light from a time when the universe had cooled enough for radiation to travel freely through space, later stretched into microwaves by cosmic expansion. In the clean version, this becomes an elegant fact. Penzias and Wilson discovered the cosmic microwave background. But the lived story is quieter and stranger. They found a noise. They tried to remove it. They suspected the instrument, the environment, even the birds. They exhausted the nearby explanations. Only then could the signal stop being a nuisance and become evidence. The hidden failure was the failure to make the machine silent. That failure matters because silence was the practical goal. A clean receiver should not hum with unexplained excess. A well-understood system should not carry a background that cannot be traced to its parts. The noise represented imperfection until the attempts to remove imperfection revealed something much larger than the instrument. This is a different kind of discovery from the contaminated plate or the glowing screen. The plate had a visible pattern. The screen glowed before the eyes. The photographic film carried a mark. The microwave background, by contrast, was impersonal, diffuse, almost without shape. It did not appear as a single object. It was everywhere, and that everywhereness was part of what made it difficult. Human attention is drawn naturally to objects. A hand in an X-ray image, a mold colony on a dish, a mineral sample darkening a photographic plate. These things offer the mind a center. But a uniform background is harder to feel. It seems almost too plain to be profound. And yet the uniformity was itself a clue. If the signal seemed to come from every direction, if it did not belong to a local source, if it persisted beyond instrument checks and environmental explanations, then it pointed towards something not merely near the antenna, but woven through the observable universe. The small hiss in New Jersey opened onto the largest history imaginable. There is a sleep-like stillness in this idea, long after the first stars formed, long after galaxies gathered, long after planets cooled, and life appeared on at least one small world. A faint remnant of the universe's early heat continued to pass through space. It moved through darkness, through intergalactic distances, through the quiet between stars. By the time human beings built instruments delicate enough to notice it, it was nearly invisible to ordinary experience, reduced to a cold whisper in the microwave sky. And when it arrived in the machine, it sounded like a problem. That is the humility of this discovery. The universe did not come labeled. It did not say, "I am ancient light." It entered through the same pathway as interference, thermal noise, and technical inconvenience. To hear it required not mystical awe at first, but stubborn housekeeping. The story also reminds us that science is communal in ways the legends often compress. Penzias and Wilson measured the signal. The Princeton group helped connect that signal to cosmological interpretation. Earlier theoretical work had prepared the ground. Later observations would refine the measurement map, tiny variations in the background, and turn what had first appeared as a uniform hiss into one of the richest sources of information about the early universe. A discovery is rarely only the first encounter. It is the beginning of a widening conversation. That conversation would eventually help cosmologists estimate the age composition and development of the universe with increasing precision. Satellites and instruments that came later would detect small temperature fluctuations in the cosmic microwave background, tiny unevennesses that became clues to the formation of galaxies and large-scale structure. But those later achievements should not make the beginning seem cleaner than it was. The beginning was a noise that would not go away. For a long-form story about hidden failure, this case is especially powerful because the failure is inverted. The scientists did the responsible thing. They assumed the noise might be local. They tried to eliminate it. They cleaned, checked, recalibrated, and questioned. The breakthrough did not happen because they ignored possible error. It happened because they pursued error carefully enough to discover its limits. This is where science differs from mere surprise. A surprising result by itself can mislead. Instruments can fool their users. Patterns can arise from defects. Human beings are gifted at finding meaning too quickly. If every anomaly were embraced as revelation, science would drown in false signals. The strength of the process lies in the fact that anomalies are not simply believed, they are pressured. The cosmic microwave background survived that pressure. It remained after the obvious causes were tested. It remained after the antenna was cleaned. It remained in a form that made more sense as something cosmic than as something local. Its reliability was born not from immediate acceptance, but from failed rejection. There is a phrase sometimes used in science: a result is robust. It means the result continues to hold under different tests, different assumptions, different attempts to weaken it. The microwave background became meaningful because it proved difficult to destroy. This is a quieter kind of drama than invention or rivalry. It is the drama of persistence. The signal waits. The scientists doubt it. The equipment is inspected. The birds are removed. The expected explanations fall away one by one. Nothing explodes. No one sees a hidden world inside a hand. There is only a low, steady remainder, and the slow realization that the remainder may be older than stars. In that realization, the scale of the documentary widens. We began with a messy plate on a laboratory bench. We moved to rays passing through flesh and photographic coverings. Now the failure is no longer just inside the lab. It reaches back through cosmic time. The unwanted noise becomes a trace of the universe when it was young before Earth, before the sun, before the first human eye looked upward and wondered whether the stars had a beginning. The irony is gentle but enormous. A machine built for human communication received evidence of a much older message, not a message in the human sense, but a physical remnant. The antenna was part of a modern technological world of satellites and signals, but it opened onto a cosmic past billions of years deep. What first seemed like dirt in the measurement became one of the cleanest pieces of evidence for a hot early universe. Again, the clean legend comes later. Later, the cosmic microwave background becomes a pillar of modern cosmology. Later, Penzias and Wilson receive the Nobel Prize. Later textbooks fold the discovery into a clear sequence prediction observation confirmation. But inside the actual experience, the sequence was tangled. The observers were not looking for that exact answer. The theorists had not yet made the observation. The signal was real before it was understood. This is one of the recurring truths of discovery. Evidence can arrive before meaning. The universe can speak before the listener knows the language. A plate can darken before radioactivity has a name. A screen can glow before X-rays are understood. An antenna can hum before cosmology recognizes the sound. In each case, the first task is not to explain everything. It is to keep the evidence from being erased too soon. Penzias and Wilson's story also complicates the idea of failure in another way. Usually we think of failure as the absence of a desired result. Here, the desired result was absence itself. They wanted the noise to vanish, and it did not. The failure was a presence that would not obey the wish for cleanliness. That stubborn presence became the clue. This is why the history of science often asks for patience with discomfort. A result that does not fit can feel like an accusation. It says that the instrument is not understood, or the theory is incomplete, or the experimental environment is less controlled than hoped. It interrupts the smooth movement toward an expected conclusion. But if the interruption remains, the honest response is not to hide it. The honest response is to ask whether the interruption belongs to the world. The cosmic microwave background did belong to the world in the largest possible sense. It belonged not to the antenna, not to New Jersey, not to any one galaxy, but to the observable universe as a whole. It was a relic of conditions so early and dense that ordinary imagination struggles to approach them. It was cold by the time humans heard it, but it carried the memory of heat. In a bedtime documentary, this is perhaps one of the most peaceful images science offers the universe, not as a sudden spectacle, but as a faint background presence still surrounding us. Every room, every field, every sleeping city, every quiet hillside beneath the night sky is immersed in that old radiation. It passes unnoticed through the ordinary dark. Only instruments listen closely enough, and even instruments must be doubted before they can be trusted. That is the heart of this section. The noise that would not disappear teaches us that discovery can be born from failed removal. It shows that a scientific error is not always the thing that survives too briefly. Sometimes the suspected error survives too long. It remains after cleaning, after calculation, after suspicion, and in surviving, it becomes more than noise. The next step in the journey turns this pattern inside out once again. So far, we have followed unwanted presence's mold, where it should not be light, where it should not shine, radiation, where no one expected it, noise, where silence was desired. But sometimes the most important failure is not an unwanted presence. Sometimes it is an absence. A carefully designed experiment searches for something the age believes must be there. It looks with precision. It expects a result. And then almost impossibly, it finds nothing. That nothing will become one of the most important silences in the history of physics. After the noise that would not disappear, we come to a different kind of scientific failure. Here the problem was not an unwanted presence. It was an absence. A carefully designed experiment searched for something that many physicists believe should exist, something woven into the deepest assumptions of 19th century science. The instrument was delicate. The reasoning was serious. The expectation was clear. And yet, when the measurement was made, the expected effect was not there. This was the strange power of the Michelson-Morley experiment. It became famous not because it saw a hidden world, but because it failed to see one. It did not reveal a new ray, a new element, or a new medical tool. It did not show bones inside a hand, or the early universe inside a receiver. It found in a precise and unsettling way almost nothing. But sometimes nothing is not empty. To understand why this nothing mattered, we have to step into a world where light itself seemed to require a medium. Sound needed air or some other material through which to travel. Water waves needed water. Mechanical waves needed something to wave. So it seemed natural to many scientists that light too must move through something. That something was called the luminiferous ether. It was imagined as an invisible medium filling space, a subtle substance through which light waves traveled. It had to be strange beyond ordinary matter. It had to fill the universe, pass through bodies, allow planets to move, and still carry light with extraordinary speed. It could not be felt by the hand seen by the eye, or easily detected by ordinary means. Yet for many physicists, it made the wave theory of light feel mechanically understandable. The ether was not a foolish idea in its time. It was an attempt to make sense of light using the habits of thought available to 19th century physics. If waves needed a medium, then light seemed to need one too. The ether gave the imagination something to hold. It let scientists picture light not as a mystery moving through emptiness, but as a vibration through an unseen ocean. If the Earth moved through this ocean, then there should be a kind of ether wind. The Earth travels around the sun, and if the ether remains still while Earth moved through it, then light traveling in different directions should be affected in tiny but measurable ways. A beam of light moving with the ether wind might take a slightly different time than a beam moving across it. The difference would be incredibly small, but not necessarily beyond measurement. Albert A. Michelson believed such a measurement might be possible. Michelson was a master of precision. He was fascinated by light measurement and the possibility of using optical instruments to detect differences almost unimaginably slight. His instrument, the interferometer, split a beam of light into two paths at right angles, sent the beams along those paths, reflected them back, and recombined them. If one beam took a little longer than the other, the interference pattern should shift. The method was elegant because it turned time into pattern. No clock needed to measure the tiny delay directly. Instead, light would compare itself with itself. The returning beams would create fringes, alternating bands of light and dark. A shift in those fringes could reveal a difference in travel time. The ether wind, if present, might leave its signature in that delicate pattern. Michelson first tried a version of the experiment in 1881. Later, with Edward Morley, he repeated it more carefully in 1887 in Cleveland. The new apparatus was mounted on a massive stone slab, floating in mercury, allowing it to be rotated smoothly. As the instrument turned, the direction of the light paths changed relative to the supposed ether wind. If the ether was there, in the expected way, the fringe pattern should shift. The experiment was designed to make the invisible medium betray itself. There is something almost ceremonial about the image. A heavy stone floating on mercury, mirrors and beams of light arranged with patient precision. A room quiet enough for tiny differences to matter. The Earth itself moving through space while two men tried to catch that motion indirectly, not by watching the planet move, but by watching light return to itself. The expected shift did not appear, or more carefully, the result was far smaller than expected, too small to support the simple ether wind picture the experiment had been built to test. The apparatus had looked for a sign of Earth's motion through the ether, and the sign was not there in the required form. The experiment had found no meaningful evidence of the ether wind. At first, this was not a moment of instant revolution. That is important. The clean legend sometimes presents the Michelson-Morley experiment as if it immediately destroyed the ether and directly produced Einstein's theory of relativity. The real history was slower, less direct, and more interesting. The null result became one pressure among many pressures. It did not erase an entire worldview overnight. Physicists tried to explain it, absorb it, adjust around it. A failed expectation does not instantly produce a new universe. Instead, it creates a wound in the old one. The ether did not vanish simply because one experiment found no expected wind. The concept had deep roots. It was connected to the wave theory of light, to Maxwell's electromagnetic theory, and to a desire for mechanical explanation. Scientists are rarely eager to discard a framework that has helped organize so much thought. They look first for corrections, refinements, hidden factors, or ways the result might fit after all. Some propose that objects might contract slightly in the direction of motion through the ether. This idea, associated with George Fitzgerald and Hendrik Lorentz, could explain why the expected difference in light travel time failed to appear. If the apparatus itself changed shape as it moved through the ether, then the measurement might be canceled out. In this way, the null result did not simply end ether thinking. It inspired more subtle attempts to save it. That is how science often behaves when a major assumption is wounded. It does not collapse all at once. It develops supports. It modifies itself. It searches for ways to keep what has worked while explaining what no longer fits. Sometimes this is stubbornness. Sometimes it is caution. Often, it is both at once. The Michelson-Morley experiment sits in that uneasy space. Its failure was not loud. Nothing exploded. No spectacular image appeared. There was no mold-killing bacteria, no glowing screen, no photographic shadow of hidden radiation, no cosmic hiss filling an antenna. There was only an expected shift that did not arrive. A silence where theory had predicted a whisper. But that silence was precise. It was not ordinary ignorance. It was measured absence. It was not that no one had looked. Someone had looked very carefully with an instrument designed for the purpose, and the expected evidence still refused to appear. This kind of nothing is scientifically powerful because it is bounded by method. It says not merely we do not know, but under these conditions, if the old expectation were right in this way, we should have seen something, and we did not. That is why a null result can be so disruptive. A failed measurement can be dismissed when the method is weak, but a careful null result becomes harder to ignore. It does not give the imagination a new object. It removes support from an old one. It makes a familiar structure feel less secure. The ether had been invisible before the experiment. After the experiment, it was still invisible. But now its invisibility was not just ordinary hiddenness. It was a problem. In the years that followed, physics moved through a period of deep transformation. The nature of light, electromagnetism, motion, and time itself came under new pressure. Lorentz developed mathematical transformations that could preserve Maxwell's equations and account for the puzzling results. Others wrestled with the strange behavior of moving bodies in electromagnetic fields. Then, in 1905, Albert Einstein published his special theory of relativity. Einstein's theory did not simply say that the Michelson-Morley experiment had failed. It changed the frame of the question. It treated the speed of light in vacuum as the same for all inertial observers and reworked ideas of time and space around that principle. In this new view, the old ether wind problem no longer had the same role. One did not need to imagine the Earth plowing through a stationary light-bearing medium in order to explain light's behavior. The experiment that found nothing had helped prepare the ground for a world in which the old something was no longer necessary. Again, we should be careful. The path was not a straight line from Michelson and Morley to Einstein. Historical influence is debated in detail, and Einstein himself described the development of his ideas through broader problems in electrodynamics, not simply as a direct reaction to one experiment. But the null result became part of the atmosphere of crisis around classical physics. It was one of the signs that the inherited picture could not remain untouched. This is where the story becomes larger than ether. The Michelson-Morley experiment teaches that science does not only progress by finding new things, it also progresses by failing to find things that should have been there. A missing result can be as important as a surprising presence. It can force a community to ask whether its expectations were built on something unstable. In ordinary life, finding nothing often feels like wasting time. A search ends, a hope fades, a question seems to have led nowhere. But in science, a disciplined nothing can be a result. It can narrow the possible. It can tell researchers that one path, however elegant, is not supported. It can make room for a different kind of explanation. There is a quiet courage in accepting that kind of result. It is not the courage of announcing a spectacular discovery. It is the courage of letting absence count. A scientist may have wanted the fringe shift, expected it, designed an apparatus to see it, and still had to report that it did not appear. The result was not emotionally satisfying in the simplest way. It did not hand over the ether wind. It took it away. And by taking it away, it made the question deeper. What if the Earth's motion through space could not be understood in the old terms? What if light did not behave like sound through air or ripples through water? What if time and length themselves were not as absolute as they seemed? What if the problem was not that the ether wind was hard to detect, but that the conceptual frame asking for it was beginning to fail? These are not small questions. They mark a shift from repairing an experiment to rethinking reality. The hidden failure is no longer confined to an instrument or a sample. It has moved into the architecture of thought. The experiment did not simply fail to find ether wind. It exposed the fragility of a way of imagining space motion and light. This makes Section 5 a turning point in the larger journey. So far, failure has appeared as contamination, unexpected light, invisible emissions, and stubborn noise. In those cases, something unwanted or unplanned entered the scene and had to be understood. But now the drama is different. Here, nature withholds the expected sign. The world refuses to confirm the picture humans had made of it. That refusal is not empty. It is active in its own quiet way. It tells science that not all wrong turns are filled with strange signals. Some are filled with silence. Some of the most important discoveries begin when a theory predicts a footprint and the ground remains undisturbed. The absence becomes the clue because the expectation was so strong. There is also something deeply human in this. We often want reality to reward the questions we know how to ask. We build our instruments around those questions. We sharpen our methods. We look carefully, honestly, repeatedly. And sometimes the answer we receive is not a new object, but the collapse of the question. That collapse can feel like failure before it feels like freedom. For physicists at the edge of the 20th century, the old world was not simply discarded. It was revised, stretched, defended, questioned, and slowly reconfigured. That is why scientific revolutions are rarely as clean as their later diagrams. They are not moments when everyone suddenly stops believing one thing and starts believing another. They are periods when many careful results make the old language harder and harder to speak. The Michelson-Morley experiment was one of those careful results. It did not shout. It waited. Its importance grew as physics continued to struggle with light and motion. It became part of a larger pattern, one in which Maxwell's equations, Lorentz's transformations, Einstein's relativity, and the failure to detect ether wind all belong to the same historical weather. A null result became a pressure in the atmosphere. That pressure changed what future scientists could ask. Once the old ether picture weakened, the path opened toward a different understanding of invariance, simultaneity, time dilation, length contraction, and the structure of space-time. These ideas would later sound almost abstract, even dreamlike. but behind them was a practical, experimental fact. A predicted shift did not appear. The hidden failures behind discovery are often like this. At first, they seem small compared to the theories they disturb. A plate is contaminated. A screen glows. A signal hums. A fringe does not shift. But if the small thing is real, and if it is followed carefully, it can force the large thing to change. This is the humility built into experiment. Theory gives science vision. It offers patterns, explanations, and expectations. Without theory, facts remain scattered. But experiment has the power to embarrass theory. It can say quietly and without rhetoric that the world did not behave as expected. When that happens, the theory must either adapt or lose its authority. The experiment that found nothing did exactly that. It did not give physics a ready-made replacement. It did not tell scientists immediately how to think about time. It did not write relativity by itself. What it did was more subtle and perhaps more unsettling. It made a confident expectation fail under careful observation. In the history of science, that can be enough to begin a transformation. As we leave this section, the meaning of failure has widened again. It is not only a spoiled sample, not only a strange glow, not only an unwanted noise. It can be the absence of something expected so strongly that its absence becomes a message. But there is another kind of failure still waiting. Sometimes science does not reject an idea because the idea is worthless. Sometimes an idea contains something powerful, even something true, but arrives before its time. It lacks the right mechanism, the right instruments, the right community, or the right language. It waits in the margins, not dead, but unable to become convincing. The next stories are about truths that arrive too early and the long silence they had to survive before the world could hear them. After the experiment that found nothing, failure has become harder to recognize. It is no longer only a spoiled plate, a strange glow, a stubborn noise, or an expected result that refuses to appear. Now we enter a quieter kind of failure, the failure of timing. An idea may contain something powerful, perhaps even something true, and still fail to convince the world because it arrives before the right tools, before the right evidence, before the right mechanism, or before the right scientific language exists to hold it. This kind of failure can look from the outside like rejection. A person proposes something the community resists, and later history gives the person credit. It is tempting to turn such stories into simple morality, plays the lone genius sees the truth. The narrow-minded world laughs, and the future proves the genius right. But science is rarely that simple. Sometimes the world resists because it is stubborn. Sometimes it resists because the evidence is incomplete. Sometimes it resists because the new idea is partly right, but not yet strong enough to stand. A theory can be visionary and still underbuilt. It can point in the right direction while failing to explain how reality could actually work. Alfred Wegener's theory of continental drift belongs to this difficult middle ground. At the beginning of the 20th century, maps of the world already held a quiet visual puzzle. The coastlines of South America and Africa seemed to fit together with strange elegance, as if two separated edges had once belonged to a larger shape. This observation was not entirely new. Others had noticed the resemblance before Wegener, but Wegener tried to make the resemblance part of a larger argument. He was not trained as a traditional geologist. He worked in meteorology and polar research fields that gave him a broad view of climate ice atmosphere and the shape of Earth's surface. He was interested in patterns across distance. He could look at scattered evidence and ask whether the separation between continents was not as permanent as it seemed. In 1912, and more fully in his later work, Wegener proposed that the continents had once been joined in a supercontinent later called Pangaea and had gradually drifted apart. The idea was startling because it made the surface of Earth feel alive in a new way. Continents, which seemed like the most stable things imaginable, were not fixed. They had moved across geological time. The solid ground beneath human feet became in this vision part of a long and restless history. Wegener gathered several kinds of evidence. The matching shapes of continents were only the beginning. Similar fossils appeared on continents now separated by oceans, such as Mesosaurus in South America and Africa. Geological formations seemed to continue across present-day coastlines, as if mountain belts and rock layers had once been joined. Ancient climate clues also appeared in strange places, with signs of past glaciation and tropical life, distributed in ways that made more sense if continents had once occupied different positions. The argument had a powerful visual and narrative force. Pieces of the world seemed to be asking to be reassembled, but there was a serious problem. Wegener did not have a convincing mechanism. He could argue that continents had drifted, but he could not adequately explain how they had moved. What force could push continents through the ocean floor? How could such enormous masses travel across the planet without leaving the kind of destruction geologists expected? Some of the mechanisms he suggested involving forces related to Earth's rotation and tides were too weak to do the job. To many geologists, this was not a small weakness. It was central. A theory in science cannot live on pattern alone. Patterns can suggest, they can tempt, they can even open a new way of seeing. But if the proposed process cannot work physically, the theory remains vulnerable. Wegener had assembled a striking map of clues, yet the machinery behind the map was missing. This is where the clean legend often becomes unfair. It is easy to say that Wegener was right and his critics were wrong. In one broad sense, that is true. Continents do move, and the fixed continent view did give way. But many critics were not simply blind. They were asking a reasonable scientific question: what is the mechanism? Without a mechanism, continental drift could look like a beautiful arrangement of coincidences rather than a durable theory. Wegener's idea was too strong to vanish completely, but too incomplete to win. That is the painful space of a truth arriving early. It can gather evidence around itself. It can attract a few supporters. It can remain visible in the literature. But it cannot yet reorganize the field, because the field does not have the instrument's data or theoretical structure needed to make it unavoidable. For decades, continental drift remained controversial, often dismissed or marginalized by many geologists. Wegener died in 1930, long before the full transformation of Earth science took place. He did not live to see the ocean floor mapped in new ways, or the evidence of seafloor spreading, or the magnetic stripes on the seabed that helped reveal how new crust forms and moves away from mid-ocean ridges. Those later discoveries changed the ground beneath the old debate. The ocean floor, once poorly known, became a place where the missing mechanism could begin to appear. The idea of seafloor spreading, associated especially with Harry Hess and others, suggested that new crust forms at mid-ocean ridges and moves outward. Paleomagnetic evidence showed patterns of magnetic reversals recorded in rocks, mirrored on either side of ridges like a slow geological tape recording. Subduction zones helped explain where old crust went. The continents were not plowing alone through a passive ocean floor. They were part of moving plates. Plate tectonics gave continental drift a stronger home. It did not simply vindicate every detail of Wegener's original proposal, it transformed the question. The movement of continents became part of a larger system involving oceanic crust mantle dynamics, plate boundaries, earthquakes, volcanoes, mountain building, and the recycling of Earth's outer shell. Wegener had seen part of the pattern before the full machine was visible. That is why his story is so useful for this documentary. It is not simply a story about a rejected genius. It is a story about the difference between being suggestive and being convincing, between seeing a shape and explaining the motion that made it. The failure was not that the idea was worthless. The failure was that the idea did not yet have enough world around it. Something similar, though, in a very different field, happened with Gregor Mendel. Mendel's story begins not with continents moving across the earth, but with pea plants in a monastery garden. It seems at first smaller and quieter. Instead of oceans and fossils, there are seeds, flowers, color, height, and the patient counting of traits across generations. But the quietness is deceptive. Inside those counts was a new way of thinking about inheritance. In the 1860s, Mendel studied how traits passed from parent plants to offspring. He crossed pea plants with different characteristics and counted the patterns that appeared in later generations. He noticed regularities. Traits did not simply blend into a vague mixture, as many people might have assumed. They appeared and disappeared in ratios that suggested inheritance was carried by discrete factors. Today, this sounds foundational because modern genetics grew around ideas like this. But in Mendel's own time, his work did not produce an immediate revolution. He presented his findings and published them, but they did not reshape biology while he was alive. His paper existed. It was available. It was not completely hidden in a literal sense. Yet its meaning did not enter the center of biological thought in the way it later would. Again, the easy legend says, Mendel discovered genetics and the world ignored him. There is truth in that, but it is not enough. The deeper story asks why the work did not land. Part of the answer lies in context. 19th century biology was preoccupied with different questions, especially after Darwin's theory of evolution raised enormous problems about variation adaptation and species change. Inheritance mattered, but the conceptual tools for connecting Mendel's ratios to broader biological theory were not yet fully in place. Mendel's work was also unusual in its style. It was quantitative, controlled, and mathematical, in a field where many naturalists worked through description, comparison, and observation of variation in the natural world. His pea experiments created a simplified system in which specific traits could be followed with clarity. That clarity was powerful, but it also made the work easier to misunderstand or underestimate. It did not yet look like the key to all heredity. A result can be precise and still fail to speak loudly to its time. Mendel himself did not use the later language of genes, chromosomes, DNA, or molecular inheritance. He spoke of factors. The physical basis of those factors was unknown. Cell biology and chromosome theory had not yet developed enough to give his patterns a visible mechanism. As with Wegener, the pattern was there before the machinery was understood. This is one of the most important parallels between them. Wegener had continents that seemed to fit fossils that crossed oceans and climate clues that made old maps tremble. Mendel had ratios that suggested inheritance moved in discrete units. Both saw order where others did not yet see enough reason to reorganize a field. Both lacked in their own different ways the later mechanism that would make the order feel unavoidable. Mendel's work was rediscovered around 1900 by scientists such as Hugo de Vries, Karl Korens, and Erich von Tschermak at a time when biology was more ready to receive it. The questions had shifted. Experimental breeding cytology and debates about inheritance had created a new context. Suddenly, Mendel's ratios were no longer an isolated pattern. They became part of a growing structure. The discovery had been waiting, but not passively. It sat in the literature like a seed that had not yet found the right season. That metaphor is almost too neat, but in Mendel's case, it is hard to avoid. The work was alive with meaning, but the surrounding scientific climate had not yet allowed it to germinate. This does not mean science failed completely by not recognizing him at once. It means that scientific recognition depends on more than truth alone. It depends on relevance, language methods, networks, questions, and the ability of one result to connect with others. That is a difficult lesson. We like to imagine truth as self-evident. Once discovered, it should shine. It should compel belief. But many truths do not shine on their own. They need instruments to make them visible, theories to make them intelligible, and communities to make them durable. Without those supports, even careful work can remain strangely quiet. Wegener and Mendel both show that science has a memory problem as well as a discovery problem. The first problem is finding something. The second is keeping it available until it can be understood. Some ideas disappear because they are wrong. Others disappear because they are incomplete. Others remain nearby, half seen, until the field changes around them. The archive of science is full not only of errors, but of possibilities that needed later conditions to become meaningful. This is not an argument against skepticism. In fact, it shows why skepticism matters. If every striking pattern were accepted immediately, science would be overwhelmed by premature theories. Wegener's critics were right to demand a mechanism. Mendel's contemporaries were not automatically foolish for failing to build a new biology around a paper whose larger implications were not yet clear. Scientific caution protects knowledge from fantasy, but caution has its own cost. It can delay recognition. It can cause a field to miss something fertile. It can leave a correct idea outside the main current for decades. Science needs skepticism, but it also needs ways to remember the anomalies, the rejected patterns, and the unfinished ideas that may later prove important. The truth that arrives too early must survive both doubt and neglect. This is a different emotional shape from earlier discoveries. The contaminated plate had to survive being discarded. The strange rays had to survive being explained away. The cosmic noise had to survive attempts to remove it. The null result had to survive the disappointment of finding nothing. Here, the idea itself must survive time. It must wait. There is a particular loneliness in that kind of waiting. Wegener did not live to see plate tectonics transform Earth science. Mendel did not live to see genetics become one of the central languages of modern biology. The later recognition of their work can feel satisfying to us, but it did not repair the silence of their own lifetimes. History can honor someone too late to be heard by them, and yet the delayed recognition still matters. It shows that science is not only a machine for immediate judgment. It can return to old evidence. It can reread neglected work. It can make new connections after decades. It can discover, sometimes with humility, that a rejected or ignored idea contains something the earlier field could not use. This capacity to return is one of science's quiet strengths. A result does not always die because it fails to convince at first. It may wait in papers, in books, in data, in maps, in ratios, in observations that seem too strange or too incomplete. Later tools may make it visible. Later theories may give it a home. Later communities may recognize what the first community could not. This does not make science heroic in a simple way. It makes it human. Human beings misunderstand timing. We confuse what is unconvincing now with what will always be false. We mistake the limits of our present tools for the limits of reality. We demand mechanisms because we should, but sometimes the mechanism is still beyond reach. We need evidence strong enough to protect us from illusion, but the strongest evidence may not yet exist. So, the story of early truth is always double. On one side, it warns against premature certainty. Wegener needed more than resemblance and distribution patterns. Mendel's ratios needed a larger biological framework. On the other side, it warns against forgetting too quickly. A partially supported idea may deserve a place in memory not as accepted truth, but as a question kept alive. That balance is hard. It is also deeply scientific. The hidden failure here is not a single error. It is the mismatch between insight and infrastructure. The idea sees farther than the tools can reach. The data point toward a pattern, but the mechanism remains out of sight. The result is careful, but the field is listening for something else. In such moments, discovery becomes less like a flash and more like a delayed conversation across generations. Wegener speaks from maps, fossils, rocks, and climate clues. Decades later, the ocean floor answers with ridges, magnetic stripes, and moving plates. Mendel speaks from pea plants and ratios. Decades later, chromosomes, genes, and modern genetics answer in a language he could not have possessed. The first voice was not complete. The later answer was not independent. The discovery belongs to the space between them. That space is where the clean legend once again fails us. If we say only that Wegener was right, we miss the reason he could not fully convince. If we say only that Mendel was ignored, we miss the fact that science had not yet built the conceptual world in which his work could become central. Their stories are not simple tales of triumph over foolishness. They are tales of timing evidence, mechanism, and memory. They show that truth may need a future, and this changes how we understand scientific failure. A failed theory may not be entirely wrong. An ignored paper may not be empty. An incomplete mechanism may not erase the value of a pattern. Sometimes, failure is the form a discovery takes while waiting for the rest of science to catch up. But once science becomes a community across time, another question appears. If recognition depends on tools, institutions, networks, and memory, then discovery is never only about ideas. It is also about people. Who gets heard? Who gets cited? Who gets trusted? Who has access to the evidence, the instruments, the rooms where decisions are made, and the stories that later become famous? The next part of the journey turns from ideas that arrived too early to people who were present at the breakthrough, but later found themselves left outside the legend. After truths that arrive too early, we come to another kind of hidden failure. This one is not a failed experiment, not a missing mechanism, not a signal mistaken for noise, and not an idea waiting decades for the right tools. It is a failure of memory. A discovery happens, the evidence gathers, the model takes shape, the world changes, and then history begins to decide who will stand in the light. The clean legend of discovery usually prefers a small cast. It likes one or two names. It likes a room, a model, a moment, when everything suddenly fits. It likes the image of a breakthrough becoming clear in the minds of a few unusually gifted people. That kind of story is easy to remember, and sometimes it is not entirely wrong. But it often leaves behind the slower, more crowded reality, the data produced by someone else, the measurements refined over years, the technicians, students, collaborators, rivals, and institutions that made the final leap possible. Few modern scientific stories reveal this tension more clearly than the discovery of the structure of DNA. Today, the double helix is one of the most recognizable images in science. Two twisting strands paired and ladder-like, carrying the instructions of life. It appears in textbooks, laboratories, films, logos, classrooms, and popular imagination. It is not only a scientific structure, it has become a symbol of identity, inheritance, medicine, ancestry, and the deep code of living things. But before DNA became an icon, it was a problem. Scientists knew that hereditary information had to be carried somehow from one generation to another. By the mid-20th century, evidence was accumulating that DNA, not protein, was the key molecule of inheritance. Yet knowing that DNA mattered was not the same as knowing how it worked. The molecule's shape was still uncertain, and in biology, shape can be destiny. A structure can explain a function before words fully catch up. The race to understand DNA was not isolated in one room. It involved Cambridge King's College London and other scientific centers. It involved chemistry, physics, biology, mathematics, X-ray crystallography, model building, and a great deal of competition. It also involved personalities, institutional tensions, miscommunication, ambition, and unequal recognition. The molecule itself was hidden inside fibers and diffraction patterns. To see it, scientists could not simply look. They had to make it cast a shadow in X-rays, then learn to read that shadow. At King's College, London, Rosalind Franklin brought unusual skill to this problem. Franklin was trained in physical chemistry and had strong experience with the structure of carbon materials. She was precise, rigorous, and cautious in the best scientific sense. She understood that a beautiful model was not enough if the evidence did not support it. Her work on DNA fibers, together with Raymond Gosling, produced some of the most important X-ray diffraction data in the story. Among these images was the now famous photograph 51. It was not a photograph in the ordinary sense. It did not show DNA as a visible spiral the way an illustration might. It showed an X-shaped diffraction pattern, a trace left by X-rays passing through ordered DNA fibers. To someone trained in the field, the pattern carried structural information. It suggested a helical form. It offered clues about dimension, symmetry, and the arrangement of the molecule. But scientific evidence does not speak equally to everyone. A pattern must be interpreted. A photograph must be connected to measurements, mathematical reasoning, chemical constraints, and competing models. Franklin's data were not a decorative detail beside the discovery. They were part of the ground on which a correct model could stand. At Cambridge, James Watson and Francis Crick were approaching the DNA problem through model building. They were not gathering the same kind of experimental data themselves. Instead, they tried to bring together existing evidence, chemical knowledge, and structural reasoning to imagine a molecular arrangement that could make sense. This method could be powerful, but it could also be risky. A model can become seductive before it becomes true. The danger of model building is that elegance can outrun evidence. Watson and Crick had already made an incorrect model before the final double helix. It was not simply that they saw the answer instantly. They tried, failed, were corrected, and had to wait for better constraints. The clean legend often compresses this. It remembers the final model, the cardboard and metal pieces, the sudden fit. But the final fit was possible because earlier attempts had been wrong. Here again, failure plays a quiet role. A wrong model is not always useless. It can reveal what a model must not do. It can show where the chemistry is impossible, where the measurements do not match, where an assumption is too eager. But only if the builders are forced back toward evidence. Without that pressure model, building can become imagination wearing the clothes of science. Franklin's evidence was part of that pressure. The history of how Watson and Crick gained access to information from King's College has been debated for decades. Watson saw photograph 51 after Maurice Wilkins showed it to him, and Crick also had access to a report containing important data from Franklin's work. The ethics and context of this access remain part of the story's unease. It is not necessary to flatten the history into a simple theft narrative to see that the flow of information was unequal and poorly acknowledged. What matters for this documentary is the shape of recognition. Watson and Crick built the model that became famous. Their 1953 paper in Nature proposed the double helix and included the understated sentence that the structure suggested a copying mechanism for genetic material. In the same issue, papers from Wilkins and from Franklin and Gosling appeared with experimental evidence. The publication itself was not a single voice. It was a cluster of related work. But public memory did not preserve the cluster equally. The double helix became attached most strongly to Watson and Crick. Their model stood at the center of the story. Wilkins received recognition as well, later sharing the Nobel Prize with Watson and Crick in 1962. Franklin did not. She had died of ovarian cancer in 1958 at only 37, and Nobel Prizes are not awarded posthumously. That fact explains part of the absence, but not all of it. Even if Franklin could not have received the Nobel after her death, the larger cultural memory still had choices to make. It could have remembered DNA as a discovery built from model and measurement together. It could have taught the story as a convergence of experimental rigor and structural imagination. It could have placed Franklin not as a footnote, not as a tragic figure at the edge of the room, but as one of the central scientific minds whose work helped make the answer possible. For a long time, that did not happen clearly enough. The hidden failure here is not the failure to discover DNA's structure. The structure was found. The model was brilliant. Its biological implications were profound. The failure lies in the later simplification, in the way a complex discovery became a story of a few names and a single dramatic insight, while the evidence that made the insight reliable was pushed toward the margins. This is how legends clean themselves. They remove awkwardness. They soften institutional tensions. They reduce collaboration into a scene. They turn data into background, and background into silence. They make science look more solitary than it is, more decisive than it was, and more fair than it may have been. Franklin's case is often told today as a correction to that silence, and that correction matters. But even here, caution is needed. It would be too easy to replace one simplified legend with another Watson and Crick as villains, Franklin as the sole true discoverer, everyone else as shadows. That would not make the history more honest. It would simply make it dramatic in another direction. The more truthful version is harder and more interesting. Franklin was not merely a victim of a story. She was a serious scientist doing difficult work under difficult conditions. Watson and Crick were not merely lucky opportunists. They had genuine insight into how pieces of evidence could be assembled into a model. Wilkins was not merely a side character. Gosling's role as Franklin's graduate student also belongs to the structure of the story. The breakthrough emerged from competition, partial access, uneven credit, and a scientific community trying to solve a problem larger than any one person. That complexity is precisely the point. If we only ask who discovered the double helix, we may end up with a short answer. If we ask how the discovery became possible, the answer expands. It includes X-ray diffraction patterns, chemical rules-based pairing, failed models, institutional rivalry, unpublished data, conversations, reports, photographs, and people whose work became necessary even when their names did not become equally famous. This wider answer does not weaken the discovery, it strengthens it. A scientific breakthrough is not less impressive because it required many hands and minds. It is more impressive because it shows how difficult nature can be to read. DNA did not reveal itself to a single glance. It had to be approached through instruments, mathematics, physical chemistry, biological urgency, and competing interpretations. The model was elegant because so much hidden labor made elegance possible. That hidden labor is often where recognition becomes unfair. Some forms of scientific work are easier to celebrate than others. The person who proposes the final model may be remembered more vividly than the person who produces the measurements. The person who writes the bold paper may become more famous than the person whose caution prevented error. The person who tells the story later may shape public memory more strongly than the person who created the evidence. This is not only a question of DNA, it is a pattern across science. Experimentalists, technicians, assistants, students, instrument makers, data analysts, and collaborators can be essential without becoming symbolic. Their work may be too distributed, too technical, too quiet, or too difficult to fit into the heroic story. The public wants a face. Science often requires a network, and when history chooses the face too quickly, the network disappears. In the case of DNA, gender also shaped the atmosphere in ways that cannot be ignored. Franklin worked in a scientific culture where women often faced barriers to authority, collegial respect, and institutional belonging. The details of her relationships with colleagues were complex, but the broader context mattered. Recognition does not happen in a vacuum. It moves through social structures, expectations, and rooms where some people are more easily heard than others. This is another hidden failure behind discovery, not failure of intelligence, but failure of listening. A community can have evidence in front of it and still undervalue the person who produced it. A discovery can rely on someone's precision and still give cultural glory elsewhere. A scientist can be central to the process and peripheral in the legend. The double helix became a clean emblem of life's code, but the history behind it remained tangled. That tangled history also reminds us that science and storytelling are not the same thing. The scientific structure of DNA did not become false because its discovery story was messy. The double helix remains one of the great achievements of modern biology. But the story of how it was found tells us something else. The production of knowledge and the distribution of credit follow different rules. Nature may give evidence, humans decide how to remember. This decision can change over time. Franklin's role is much more widely recognized now than it was in earlier popular accounts. Photograph 51 has become famous in its own right. Books, plays, articles, and histories have returned to her work and asked what the clean legend left out. In this sense, science's self-correcting impulse can extend beyond experiments into memory. The record can be revisited. The cast can be widened. The hidden labor can be brought back into view. But correction after the fact is still correction after loss. Franklin did not live to see how central her work would become in public memory. Like Mendel and Wegener, In a different way, she was fully recognized by many later listeners only after the moment when recognition could have changed her lived experience. History can restore a name, but it cannot return time. There is a quiet sadness in that. Yet there is also a necessary clarity. To tell the story more fully is not only to honor one person, it is to understand discovery better. It teaches us that scientific truth may emerge from a process that is both rigorous and socially imperfect. The data can be strong while the credit is uneven. The model can be right while the memory is incomplete. The breakthrough can be real while the legend is too narrow. That is why this section belongs near the end of the journey. We have seen failed-looking objects become clues. We have seen old theories crack under missing evidence. We have seen ideas arrive before their time. Now we see that even when discovery succeeds, another failure may begin afterward, the failure to remember all the conditions that made success possible. The messy room is not only the laboratory, it is also the archive, the lecture hall, the prize ceremony, the textbook, the documentary, the story told to children about how knowledge advances. Every time a complex discovery is turned into a simple legend, someone or something may be left outside the frame. Sometimes simplification is necessary. No story can hold everything. But there is a difference between simplifying and erasing. A good history does not need to name every person in every room, but it should not pretend that a room with many minds had only one or two. The double helix asks us to look again at the shape of fame. A helix itself is not a straight line. It twists around an axis, two strands bound together, each giving meaning to the other. There is an accidental beauty in this. The symbol most associated with modern genetics also gives us a way to think about discovery not as one strand of genius, but as intertwined lines of evidence, interpretation, labor, rivalry, and memory. Pull one strand too hard and the structure is distorted. So perhaps the more mature version of the DNA story is not less wondrous than the clean version. It is more wondrous because it is more human. It contains brilliance and ambition, rigor and rivalry, insight and unfairness, precision and haste. It shows science moving forward, not as a pure beam of light, but as a human enterprise, carrying both extraordinary power and ordinary flaws. This does not make science untrustworthy. It makes the need for correction even clearer. If science can correct theories, it must also learn to correct stories. If it can return to data, it can return to memory. If it can test a model against evidence, it can test a legend against the fuller record. The same humility that makes a scientist ask whether a result is wrong can make a culture ask whether its version of a discovery is too narrow. And when that happens, the hidden people begin to reappear. They do not replace the famous names. They complicate them. They restore proportion. They remind us that discovery is not only the moment when truth becomes visible, but also the long process by which the people who helped reveal it are finally seen. From here, the documentary turns toward its final question. We have followed contamination, strange light, unwanted noise, measured absence, ideas that waited for the future, and people left outside the legend. At every stage, failure has changed form. It has been technical, intellectual, social, historical, and human. So, if science contains all of this, why does it not collapse under its own messiness? The answer is not that science is pure. It is that science at its best can return to what it missed. It can revisit the plate, the photograph, the signal, the null result, the old paper, the overlooked contributor. It can ask again. It can correct not only what it knows, but how it remembers knowing it. By now, failure has changed shape many times. It has appeared as a contaminated plate, a glow in a darkened room, a photographic mark made without the expected light, a signal that would not disappear, an experiment that found nothing, an idea that arrived before its mechanism, and a scientist whose work stood too long outside the central legend. Each form of failure looked different from the others. Some were technical, some were theoretical, some belonged to timing, some belonged to memory. But together they lead back to the same question. If science contains so much error, uncertainty, delay, rivalry, accident, and unfairness, why does it not collapse under the weight of its own messiness? Why does a process so full of wrong turns still become one of the most reliable ways human beings have found to approach the truth? The answer begins with a simple but important distinction. Science is not reliable because scientists are never wrong. Scientists are human. They misread evidence. They defend familiar ideas. They become attached to theories. They overlook people. They work with imperfect instruments and incomplete language. They live inside the assumptions of their own time. Science is reliable when it is working at its best because it does not have to protect every mistake forever. It can return. That may be the quietest and strongest thing about the whole story. Science can return to the spoiled plate, the strange signal, the failed prediction, the old paper, the forgotten photograph, the person who was left outside the frame. It can look again with sharper tools, better questions, wider evidence, and sometimes greater humility. This capacity to return does not make science perfect. It makes it corrigible. It means knowledge is not supposed to remain frozen at the first interpretation. A result can be questioned. A theory can be revised. A claim can be tested by another hand in another room. An old dismissal can be reconsidered when new evidence appears. That is why failure does not break science. Failure becomes dangerous only when it is hidden, protected from criticism, or turned into dogma. When failure is exposed to method, it can become useful. It can show where an assumption is weak. It can reveal that an instrument is not understood. It can mark the edge of a theory's reach. The contaminated plate showed this in one way. If Fleming had simply thrown the dish away, the mold would have remained only a nuisance. But because the pattern was noticed, because the strange zone around the mold was kept long enough to be examined, the failure changed category. It became a clue. Still, the clue itself was not enough. Penicillin had to pass through years of chemistry testing, purification production, and clinical work before it could become medicine. The science did not rest on the charm of the accident. It rested on the work that followed. The same is true of the strange light that led to X-rays and the darkened plates that led to radioactivity. A glow or stain by itself could be misleading. The first interpretation might be wrong. The effect might be trivial, local, or misunderstood. But when Röntgen investigated the rays carefully, and when Becquerel followed the uranium effect beyond his original expectation, the anomaly became more than a curiosity. It survived attention. That phrase matters. A result must survive attention before it can become knowledge. It must survive doubt, repetition, comparison, and attempts to explain it away. Science does not honor the anomaly because it is strange. It honors the anomaly only when strangeness continues to hold under pressure. The cosmic microwave background made this even clearer. Penzias and Wilson did not immediately celebrate their unwanted noise. They tried to remove it. They checked the instrument, the environment, the antenna, the ordinary sources of interference. In doing so, they treated the noise not as a mystical whisper, but as a suspected error. Only after the suspected error refused to vanish could it become evidence. This is a crucial point. Science does not become trustworthy by believing every surprising thing. It becomes trustworthy by making surprising things earn their place. The noise in the antenna mattered because it remained after reasonable doubts had been pursued. The suspected mistake became a signal because it could not be reduced to the usual mistakes. Then came the experiment that found nothing. The Michelson-Morley result showed that absence can also become knowledge when it is carefully measured. The missing ether wind was not just a lack of information. It was a result that placed pressure on a major assumption. It did not instantly create a new physics by itself, but it helped make the old picture harder to maintain. A theory had expected the world to leave a mark. The mark did not appear. This kind of failure is deeply important because it protects science from becoming only a search for confirmation. If experiments only mattered when they found what theory wanted, science would become a mirror for its own expectations. But the great power of experiment is that nature can refuse the question. It can say no. It can leave silence where a theory predicted a voice. That refusal can be painful, but it is also liberating. It frees science from ideas that once seemed necessary. It opens a space where a stranger, deeper explanation can begin. Wegener and Mendel showed another side of the same process. Sometimes science does not recognize something quickly, not because the evidence is worthless, but because the surrounding world is not ready to make sense of it. Wegener saw a pattern in continents, fossils, rocks, and ancient climates, but his mechanism was too weak to persuade many geologists. Mendel found mathematical order in inheritance, but biology did not yet have the conceptual machinery to make his work central. Their stories are not simple accusations against the past. They are reminders that recognition depends on context. A scientific truth may need instruments that do not yet exist. It may need a theory not yet formed. It may need a community asking the right question. It may need time. This is frustrating, sometimes tragic, but it also shows that science is larger than any single moment of judgment. Later generations can reopen what earlier generations could not use. Then Rosalind Franklin's story brought the question into the realm of memory. Here the failure was not that DNA's structure remained undiscovered. The double helix was found, and it became one of the great achievements of modern biology. But the story of how it was found became too narrow. The evidence, the diffraction images, the careful measurements, and the work of people outside the main spotlight were not remembered with equal force. This kind of failure does not always change the scientific result, but it changes the moral and historical truth around the result. A correct model can still have an incomplete story. A breakthrough can be real while its legend is unfair. A structure can be right while the memory of the people who helped reveal it is wrong. If science is committed to correction, that correction cannot stop at equations and experiments. It must also reach the stories told about discovery. This does not mean every historical account can become perfect. No story can include every name, every room, every note, every delay, every disagreement. But it does mean that the clean legend should never be mistaken for the whole truth. The legend is a doorway, not the room itself. And the room itself is always messier. This messiness is not a weakness to be hidden. It is the condition under which science actually works. Instruments misbehave, but their misbehavior can reveal limits. Theories fail, but their failure can make assumptions visible. People compete, but competition can sharpen questions and also distort credit. Communities resist new ideas, but resistance can protect against fantasy and also delay recognition. The same forces that make science difficult also make it human. This is why a mature view of science should be neither cynical nor naive. Cynicism says that because science is full of error, it is only another story people tell themselves. Naivety says that because science produces knowledge, its path must be clean and its heroes must be pure. Neither view is strong enough for the real history. The real history asks for something steadier. It asks us to see that science is a human practice, disciplined by methods that no single human fully controls. A scientist may be biased, but another scientist can test the result. A theory may be beloved, but an experiment can embarrass it. A discovery may be misremembered, but historians and scientists can return to the archive. A result may be ignored, but later evidence can bring it back. Science does not remove human fallibility. It builds procedures that can sometimes outlive it. This is why replication matters. It is why measurement matters. It is why open criticism matters. It is why peer review, imperfect as it is, matters. It is why instruments are calibrated, why methods are described, why data are debated, why old conclusions are revised when new evidence demands it. These practices do not make science smooth. They make it able to recover. Recovery is the deeper word. A failed experiment can recover meaning. An ignored idea can recover relevance. A forgotten contributor can recover visibility. A wrong theory can leave behind a better question. A spoiled sample can recover value when someone notices that its pattern is not random. In each case, failure is not automatically noble. Many failures remain failures. Many wrong ideas are simply wrong. Many anomalies dissolve when measured more carefully. Many exciting clues disappear under better evidence. That, too, is part of the process. The value of science lies not in pretending that every mistake hides a discovery, but in creating ways to tell the difference. That difference is hard to find. It requires patience with uncertainty, but also discipline against fantasy. It requires openness to surprise, but also skepticism toward surprise. It requires imagination, but also restraint. It requires the courage to follow a strange result, and the courage to let it go if it does not survive. This balance is fragile. It has to be practiced again and again. Perhaps that is why the clean legends remain so tempting. They spare us the difficulty of balance. They give us simple certainty after the fact. They tell us that the important result was obviously important, that the right person saw it clearly, that the world changed in a single line. They turn science into a sequence of bright rooms. But the real rooms were dimmer. In those rooms, someone had to decide whether a contaminated dish deserved a second look. Someone had to sit with a glowing screen before the nature of the ray was known. Someone had to develop a photographic plate that should not have been marked. Someone had to keep chasing a noise through every possible source until the noise became cosmic. Someone had to accept that an elegant experiment had not found the thing it was built to find. And beyond those rooms, someone had to keep an old idea alive long enough for the ocean floor to reveal its motion. Someone had to reread a neglected paper on pea plants after biology had changed around it. Someone had to look again at the story of DNA and ask who had been left outside the frame. This is the larger pattern. Science moves forward not because every step is wise, but because some steps can be retraced. It grows not only by adding knowledge, but by revising the path by which knowledge was made. It learns from the stubborn fact, the failed prediction, the delayed recognition, the missing name. That is why failure does not break science. Failure is one of the pressures that gives science its shape. A science without failure would not be stronger. It would be more fragile because it would have no way to test itself against resistance. It would become a polished surface with no scratches, but also no depth. The scratches matter. They show where reality pushed back, and reality must be allowed to push back. That may be the quiet lesson behind all these discoveries. Nature does not arrange itself around human expectations. It does not care which theory is elegant, which name is famous, which instrument was expensive, which result would be convenient. It gives signs, absences, disturbances, patterns, and refusals. Human beings then have to decide how honestly they will listen. The best of science is that listening made disciplined, not perfect listening, not innocent listening, not listening free from ambition, rivalry, error, or pride, but listening that can be challenged, repeated, corrected, and extended beyond the first listener. In this sense, the hidden failures behind famous scientific discoveries are not embarrassing footnotes to the triumph of knowledge. They are part of the structure. They show us that truth often arrives in forms that do not look like truth at first. It may come as contamination, as darkness, as silence, as delay, as another person's overlooked labor. The clean legend remembers the moment of arrival. The deeper history remembers the difficulty of recognition. And perhaps that is where the wonder becomes greatest. Not in the idea that science always knows what it is doing, but in the fact that it can move forward even when it does not. It can begin in confusion and still build clarity. It can begin in error and still produce knowledge. It can begin with human limitation and still reach beyond it. That does not happen automatically. It happens because someone pauses, someone tests, someone doubts, someone repeats, someone returns. Someone asks whether the thing that did not fit might be trying to teach the theory its own boundary. This is not a loud kind of heroism. It is quieter than that. It is the patience of a mind willing to be corrected by the world. As this journey closes, the famous discoveries may still shine, but they shine differently. Penicillin X-rays radioactivity, the cosmic microwave background, the null result of Michelson and Morley, continental drift, Mendelian inheritance, the double helix. Each is still remarkable. But now the shine comes not only from success, it comes from survival, through uncertainty. Each discovery passed in some way through a region where it could have been missed, misunderstood, dismissed, delayed, or remembered too narrowly. The fact that knowledge emerged anyway is not proof that science is simple. It is proof that science at its best can make use of difficulty without pretending difficulty is not there. So the story does not end with a perfect march toward truth. It ends in a quieter place, a laboratory bench, a dark room, an antenna pointed toward the sky, an old paper waiting to be reread, a photograph looked at again, a name restored to the story. In each place, failure remains close, but now it no longer looks only like defeat. It looks like the rough surface against which knowledge learned to become more careful, more patient, and more true. By the end of this journey, the clean legend of discovery feels a little less complete. The old version is still beautiful, but it is no longer enough. Behind every simple story, there were rooms full of hesitation instruments, that misbehaved ideas that arrived too early, results that looked useless, and people trying to decide whether a strange detail was worth keeping. That is what makes the history of science so quietly moving. It is not only a record of genius, it is a record of attention. Again and again, knowledge advanced, because someone did not throw away the spoiled plate too quickly, did not silence the signal too soon, did not ignore the result that refused to match the theory. Science moved forward not by escaping uncertainty, but by learning how to stay with it. The hidden failures behind great discoveries remind us that truth rarely enters the world already polished. It often comes as a disturbance, a wrong answer, a broken expectation, or a clue no one knows how to read yet. Only later does the story become smooth. Only later do we draw a clean line from confusion to understanding. Perhaps that is the quiet comfort in this history. To be wrong is not always to be lost. Sometimes it is the beginning of a better question. Sometimes the failed experiment, the missed meaning, the rejected theory, or the forgotten contributor becomes part of a larger pattern that no one could see at first. And so, the story of science is not a story of perfect minds moving cleanly toward perfect truth. It is a story of human beings listening carefully to the things that did not fit, and slowly learning which failures were merely failures and which ones were the first faint shape of discovery.